All right, good afternoon, everybody. Good afternoon. We're going to go ahead and get started. All right. Well, couple of things. So unfortunately, Professor Mahoney is still not feeling well enough to do lab tomorrow. So we made another online lab. Okay, so we will still have you hop on right at the start of your lab to take the quiz like you did last time with HonorLock. Okay, and then you won't need to jump onto Zoom with her like you did last time. Okay, so there'll be she'll send out an email with the instructions, but there'll be there's a note, a handout just like you would normally have, but it's just been modified for online. It'll give you the instructions on what to do. And then on Canvas, there's a thing that you answer the questions on and turn that in just like last time. Okay, so that's what we'll do again tomorrow for lab. After that, next week, hopefully she'll be back and ready to go, because next week we'll start the dissection, which we definitely don't want to do that one online. We did that once and that's not fun. So yeah, so hopefully we'll be good next week. But yeah, so that's the deal for tomorrow. For Friday, remember exam 1, and make sure to come with your laptop fully charged, ready to go. Again, if you had any issues with HonorLock when you're doing the practice quiz, get those figured out before Friday. Okay, I will give you a little piece of paper to use as scratch paper. Okay, so you can have something to write with to work on that, just in case you want to write things down during the exam or work things out or make notes to yourself on which ones to go back to. You can use that scratch paper for that, and then you'll turn it into me at the end of the test. Okay, so all right, any questions about what's going on for the rest of the week? Yeah. Yeah, so pretty much if you understand the activities that you did last time, and then you'll be fine. Yeah, it's not super hard. Okay, not super difficult. Just understand the reflexes, how those sensory receptors work, the things about, yeah, just all the little activities, and you'll be totally fine. Okay, yeah, so yeah. It's more about the activities, yeah, not so much about the introductory part, but more about the activities, reflecting on that. Yeah.
So tomorrow we do not have to go on Zoom?
You don't have to go on Zoom tomorrow. You just do the quiz right at the time that your lab would start. And then you'll have the rest of the day to turn in the lab. Okay, so the lab will be due on Canvas by 11:59 p.m. for all sections. So so you have the rest of the day to do that, but just you do need to take the quiz right at the time that your lab would be. Okay. All right. Other questions about any of that? Okay. All right. Well, today we'll dive into kind of more of the physiology of the ears, and we talked about all those little structures last time, and now we'll look at how they work a little bit more closely with this. So let's start off with the preview question, a little bit about sound here. Okay, so go ahead and yeah, talk about that with your team, and you can answer that question. That did not flip over. Wait, hold on. Oh, I got it frozen. Here we go. There we go. All right. No, still can't see it. There's the question. Answer that question. Yeah, so this will be on the next one. So talk about it with your team. Make sure you're on the same page. Now they're finished. You're one of the last ones that hasn't registered your clicker yet. Did you see my email? Yeah, you personally. Yeah, so I don't. It could be that this isn't linked up with your name, or it could be that you just haven't connected to our class yet. Oh. Okay. All right, about 10 more seconds. All right, anybody else? We got 62 of you, 63. All right, everybody got it in? Okay, guys, let's come back together. All right, so about 78% of you said E, all the above, okay? And so there is a little bit of each of these in the definition of sound. Probably the most specific, which is what we'll talk about a little bit today, is this one here, which is this alternating high and low pressure waves traveling through the particles in the air, which is definitely causes movement of air particles, causes vibration of air particles, and it really is energy passing through those. So E for sure would be correct, but we'll kind of spend some time talking about this idea of high pressure waves versus low pressure waves here in a sec. Okay, any questions on that? Okay. All right, so let's again talk about this, the physics of sound. So what is sound? Yeah, so we got these vibrations of particles in the air, okay? Maybe the more accurate one, like I just said, alternating areas of high pressure waves versus low pressure waves. Okay, and so probably one of the easiest ways to visualize this is with the example of a tuning fork. Okay, and I'll show a little video here in a sec that shows us that, but this little diagram, this little drawing here kind of shows that as well. When it's not moving, we can see the air kind of all spread out, right? That's what those lines represent, the air. When you slap a tuning fork, the little arms go back and forth like this, right? And so when those arms push outwards, what that does to the air, it compresses that air right there, right? It smashes all the air particles together that's close to that arm, okay? But then right away, that arm pulls back the other direction, right? And when it pulls back, it actually decompresses the air, pulls the air apart right next to it. Right? And it's just doing that constantly over and over and over again, right? So we get these alternating waves of high pressure, like we can see here, right? And then low pressure. So it's rarefaction for the low pressure and compression for the high pressure waves, okay? And this is exactly how a speaker works too, right? If you, like we talked about last time, if you've seen a speaker with the cover off of it before, you see that membrane moves out and then it pulls back, right? It moves out and pulls back, and it does that constantly, right? So it compresses the air when it moves out, and then it pulls back and decompresses the air when it pulls back. Okay, so let's just kind of watch a little example of that here on this video.
You booked a sunny Verbo ski chalet with endless views and snow-covered peaks.
There we go. This is a super old school video, but I still like it. There we go.
Air molecules. Every time the bonds move apart, they push against the adjacent air. In turn, this movement affects the air further on.
All right, so let's talk about frequency first, some of these properties of sound. So the definition of the frequency of sound will be a number of waves per given unit of time, okay? And the way that we're typically gonna measure that is in hertz, and hertz means waves per second. Okay, and this is what we were talking about last time when we looked at that basilar membrane and showed that the beginning of it is sensitive to 20,000 hertz, the end of it is sensitive to 20 hertz, right? So that's our audible range of sound, right? We're most sensitive to sound waves or frequency of sound kind of in the middle, but really more in 1,500 to 4,000 range. That's where most of the sounds that we interpret on a daily basis fall, okay? And for some reason, a lot of these little things, they should be arrows instead of question marks. I'm not sure why those got messed up, but so that's the frequency. And what the frequency dictates for us in the way that we hear the sound is the pitch, right? So higher frequency means the waves have higher energy to them, and those are higher pitch sounds. Okay, if it's a lower frequency, it means those are lower energy waves, and that will be a lower pitch sound or deeper sound. Okay, and the way that works in the cochlea, and we'll talk about this more, but the way that works in the cochlea is literally just the neurons that are connected to the high pitch part of the we'll put it this way, the neurons that are connected to the hair cells that are close to the high pitch part of the basilar membrane, The brain just knows when it gets action potentials from those ones that it's a high pitched sound, right? And then the brain knows that the neurons are connected to the ones that are the lower pitch. It knows when it gets action potentials from that one, that that's a lower pitch sound, right? It's not that the signal looks any different, it's just action potentials, right? But the brain knows how to interpret where that signal comes from as different pitches of sound. Okay, questions on that? Okay. All right, so that's frequency. The other thing to think about is the amplitude of sound. Okay, so definition of that is just the height of those waves, right? So when we think about it in terms of the tuning fork, it's just the harder that that tuning fork swings out, it's going to create a higher amplitude wave. Okay, and the way we measure this is in decibels. Okay, there's a measurement of how the amplitude of the sound, and what the amplitude is going to mean for us as far as the way our brain interprets it is just how loud it is, right? So if we have an increased height, higher amplitude waves, that's going to be louder noise. Okay, lower height, lower amplitude wave, that's going to be a quieter or softer noise. Okay, and the way that this happens in the cochlea is just how far those hair cells are bent, right? The stronger the sound is that comes in, the higher amplitude waves, the hair cells get bent further, right? And so you get more frequent action potentials happening on those neurons. And if the brain is receiving more frequent action potentials from a certain area, then it knows that's a louder sound, right? Okay, so that's both the frequency and the amplitude of the waves and how your brain interprets that. So take a second here and just this can probably be pretty quickly, but interpret both the top and the bottom. Which line has a higher pitch? Which line has the louder sound? And go ahead and send in the answer on your clickers to that first question there, which would be which line has the higher pitch. And talk to each other here, talk to the people on your team.
Yeah, that's why.
All right, about 10 more seconds. Got a few more of you, it looks like, to send it in. Anybody else? Good, I think that's everybody there. All right, so with that first question, 100% of you said A. You said A has a higher pitch, right? Because there's just more of them in a given period of time, right? If we say how many waves occur in 1/100th of a second, we got 1, 2 for line A and only 1 for line B, right? So that's a higher frequency with line A, right? So high frequency, low frequency. Okay, and then which line has the higher sound, A or B? A, absolutely, right? The waves are just taller, so we got higher amplitude. So A has the louder sound, okay? Some of you guys have probably seen a fake decibel meter when you go to like a basketball game or a football game, and they put it up on the big screen. They're like, you know, let's get loud, right? Third down or whatever. and it just goes up and up and up. Whether or not the crowd actually goes up, it still goes up, right? They usually kind of fake those, but yeah. You can actually download a decibel meter on your phone. I did it one time because I was installing a new bathroom fan, and our old one was just so incredibly loud that my wife just hated it. It was like so loud, so I wanted to like see how much quieter it got. So I measured it with the old one, and I measured it again with the new one, and it was quite a bit quieter. I was able to prove that to her, but yeah. So, anyways, any questions about those two concepts before we keep moving on? Okay. All right, so let's talk a little bit more about this flow of sound through the cochlea, okay? And we kind of already talked about this last time, but sound waves are going to enter through that first part, the oval window, right? And so we can see that right here in the cochlea, okay? And then they're going to travel through this upper canal, right? And then whenever they hit the range in the basilar membrane that matches the frequency that sound wave is, then it's going to pass through the basilar membrane, right? And when it passes through the basilar membrane, that's actually where the organ of Corti gets stimulated, right? It bends those hair cells, activates those neurons that are connected to that part, right? And then those neurons go up to the brain and tell it we're receiving a sound with this frequency. And so it sounds like this, right? So the location of the hair cell stimulated is dictated by the frequency of the waves, and then that dictates the pitch of the sound that we perceive in the brain. Okay, and then again, the amount of displacement, or just kind of how far those hair cells move, dictates the volume of the sound. And then again, the larger the amplitude of waves, the more displacement we get, and the more hair cells that get displaced, and so the louder sound we hear. Okay. All right, let me flip over. I have this video here.
To hear, our ears must capture sound, transmit it to the organ of Corti, and translate it into neural impulses to be delivered to the brain.
Okay. All right, so let's take a second then and have you guys turn to the people on your team and kind of fill in these steps that are going on here, right? So you can see the numbers, and then you can kind of fill in what's going on with each of those different steps. And then we'll come back together and walk through that together. Okay, go ahead. I'll put those, I'll put them in there. I'll send them to you guys. Yeah, thank you. Yeah.
Yeah, then that was great.
I think like
I don't know, I'm sure you're gonna explain it up here, but we were wondering about 4A and 4B, what the
Mhm.
distinction between those two was.
Yeah, we'll get into it. It's related to the difference between audible sound and inaudible sound. If that's a hint for you.
Okay.
Yeah.
So when it goes through all this process and then it comes out the round window,
Yeah,
is that just kind of like a release of pressure?
pretty
or like,
much. Yeah,
That's pretty much
that's
it.
pretty much what it is. Yeah.
Okay.
Mhm. Yeah.
Cool. And does that just like kind of go out into the space, or does it leave?
Yeah, it kind of just disperses through your bones, I mean, that's kind of
Okay.
even why like your head kind of almost feels like it vibrates when you have really loud sounds,
Uh-huh.
because it really does just kind of vibrate all your cranial bones.
Oh, okay.
So yeah,
Interesting.
kind of disperses through all of that. Yeah.
Okay.
Yeah.
That helps.
Imagine, like, this is the.
All right, guys, let's go ahead and come back together here. And we'll just kind of walk through these steps here. Okay, so one thing that's interesting to note here when we look at the way this works is obviously number one is just moving the tympanic membrane, right? Okay, so that's really just acting like that speaker membrane that goes back and forth, right? And the interesting thing to note is that it's way bigger than the oval window, right? And so what that does is that really amplifies the sound as it goes from the tympanic membrane to the oval window in a similar way that when we take the pressure of our whole body and we have normal shoes on and we could measure how much pressure is touching the ground with just normal shoes, that would be that the same total amount of pressure would be the same as when we're wearing ice skates, right? But if you were able to feel that amount of force underneath that ice skate, that would be a lot more pressure in that one spot, right? So it's like we're by taking the same amount of pressure, but then honing it in on one little spot, that's like amplifying the pressure, right? And that's exactly what happens when we go from that big tympanic membrane down to the small oval window, is it amplifies the pressure. Okay, so we move in the tympanic membrane, moving the auditory ossicles, right? So those things are just shaking back and forth, just like it showed in that video. Okay, and then we're going to move the round window, and then sound's going to enter the upper chamber. And I don't make you remember those scala names. That's why I have that off of there, but those were in the video. Okay, so the sound is vibrating through there. And so then in 4A, someone help us understand that. Why is it just wrapping around the back and then going right into the lower canal? What would that mean about that? We can't hear it, right? This is outside of our audible range of sound, right? There's no part of that basilar membrane that is sensitive to that frequency of sound. And so it just passes right through, right? It has an exit route. Okay, it goes through 4A, goes all the way around, back out the round window, and then that energy just kind of disperses throughout your skull, right? Okay, so this would be inaudible sound. Okay, and then 4B would be audible sound. Goes through that organ of Corti. And then it's going to activate those sensory neurons on the cochlear nerve, and then go up and tell our brain what frequency of sound we're hearing. Go ahead, Alicia.
So with high frequency, does it wrap around just the same as it would do with lower frequency? Like I know dogs kind of tie up.
You mean if it's outside of our range of hearing, but high versus low? Yeah, for sure. It'll just go all the way around. Yeah, for both. Yeah. Kat, go ahead.
So is the basilar membrane like around the organ of Corti?
So the basilar membrane is the base of the organ of Corti. Let's see if we can see it. This image kind of shows it somewhat. Yeah, so you can see it here. So here's the basilar membrane. Here's the bottom of those hair cells. So the hair cells are so here's the organ of Corti right here, right? And we're zooming in on that. This whole bottom part is the basilar membrane. And then we would also have the tectorial membrane that these tips are kind of embedded in. All right, so that basilar membrane's moving, tectorial membrane's not. So that's what bends those hair cells. Yeah, good question. Other questions? Yeah, go ahead, Mallory.
Back on that last picture, for number 2, is
Yeah.
it like saying, is it like what how is the stapes kind of like moving against the oval window?
Uh-huh.
And you said like there's the ossicles. Can you just explain it further?
Yeah, so it's just that the eardrum or the tympanic membrane is connected to the malleus, right? So when the eardrum moves, the malleus moves, right? But the malleus is connected to the incus by a little synovial joint. So when the malleus moves, the incus moves, right? And then that incus is connected to the stapes via a little synovial joint. So when the stapes moves, when the incus moves, the stapes moves. And when the stapes moves, it's connected to the oval window. So it's going to move the oval window too, right? So it's just kind of that step-by-step process. Yeah, good. Go ahead.
So do you ever see any sound in the 4A unit with like a little bent part?
In that if we were talking about the basilar membrane right here, then yes, we would hear that. But 4A is just representing the sound that went all the way around it that we didn't hear. That makes sense? That would be like our lowest frequency at the very tip, right? And then down here would be our highest frequency sound. So highest frequency is first, right? And then lowest frequency is at the very end, the very tip of it. Yeah, Mallory?
So when it shows the sound wave going through at 4B, is that like going through that cochlear duct? Or-
Absolutely. Yep. It's going through the cochlear duct, that middle part where the organ of Corti is. Good clarifications. Yeah. Other questions, Trevor?
So are the areas where we don't detect frequency, are those not innervated, or just because they don't?
So the whole organ of Corti is innervated all the way along. We have organ of Corti all the way from here, all throughout. Okay. So when it comes to what we don't hear, it doesn't even go through the organ of Corti. It just wraps around it, right? So it never passes through that middle canal. There's a little exit route for it, which I've completely covered up with pen marks at this point. But right there, right? So you can see how it doesn't have to go through it. It can just wrap around. So it never touches those hair cells. Yeah. Okay, go ahead, Annalise. They typically may have a longer basilar membrane, but also just a larger range of frequencies within their basilar membrane. Yeah. Good question. Yeah, go ahead.
So if you were gonna like damage your hearing, would that most likely happen just like at your tympanic membrane, or like could you hypothetically like rupture your organ of Corti?
Yeah, hold that question. We're gonna get to it in one sec. We're gonna talk about hearing disorders in one sec. Okay, and I'll answer that question, I think. But no, I've never heard of a ruptured organ of Corti, but you can definitely damage your hair cells for sure. Yeah, yeah. Okay, so this one just kind of shows the movement of those. Yeah, nothing more than we've already talked about. One thing to note is that what part of the brain is receiving this information and processing this information. So it's called the auditory cortex, which is part of the temporal lobe, right? And just like you guys looked at with the sensory receptors, we have a whole region of our brain that's dedicated to certain frequencies, right? So all the neurons coming from the real low frequency part end up in that part of your sensory or your auditory cortex, right? All the neurons that end up that are in the high frequency part end up on that part of your auditory cortex, and that's just the way the neurons are set up. So if that part's stimulated, then you perceive higher or lower pitch sound. Okay, so when it comes to hearing disorders, there's really two primary types. And so the first one would be called conduction deafness, right? And so this means that there's some problem in getting the sound from the external environment to your inner ear. Okay, there's a problem with conducting it. Okay, so this could be most likely a middle ear problem. It could be an external ear problem. If you got a big piece of earwax in your ear, that would also be a conduction problem too. Okay, but most of the time we're talking about a middle ear infection. Okay, otitis media. And so then this just slows down the way that those bones move. Remember, if that air-filled cavity of the middle ear becomes a fluid-filled cavity, those bones aren't going to move the same, right? So we don't have the same level of conduction that we would if it was air-filled like it's supposed to be. Okay, so that's conduction deafness. But we can also have sensory neural deafness, which means the hair cells themselves or the actual neuron pathways are damaged. Okay, so this is caused by very loud noises. It can also be caused by certain drugs getting into your ears, chemicals damaging your hair cells. So the term tinnitus is the medical term for ringing in your ears. Okay, and really what this is that you've damaged those hair cells so extremely that they got bent over so far that it could be temporary or it could be permanent, but they're always sending a signal onto the neurons, right? And so it typically tends to be the ones that are in the very first part of your cochlea, just because they kind of take the brunt of that sound because it comes in first, right? And that's the high frequency area, right? And so that's what we hear with ringing in our ears. And I always have ringing in my ears. Maybe does anybody else have tinnitus? Yeah, a couple people. Yeah. For me, it was because I grew up in the country and we shot guns a lot and we never wore ear protection. So I wasn't very smart. So my ears are permanently damaged. So I can't hear high frequencies of sound. There's been a couple times where I'm in a place like we did a tour of a ship down on Coronado one time. And there's this really high pitched sound. Everybody was like, "Oh, that's so loud." I didn't hear it at all. And so that's kind of the weird part about tinnitus is you always hear a sound. So that really means you never actually get to hear that sound when it's actually coming into your ears, right? Because you're always hearing it. So there's no difference between when it comes into your ears and when it doesn't come into your ears, right? So that can definitely be temporary, and you guys have experienced that before. Your ears kind of ring for a little while and then it goes away, but it can also be permanent if it's bad enough. Yeah. All right.
Are like hair cells like actual relation of your
No, it's just referring to those little tip links and those little cilia on top.
wondering because I know like people sometimes that like go through chemotherapy, like I was saying, like they lose their hair, but they also have ringing in their ears.
Oh, yeah. Yeah, I don't know what the ringing in the ears from chemo is caused by. It's probably related to destroying some basal cells that are there to replace some other cells, but I'm not 100% sure. Yeah, Alicia?
So how come like for you, your hair cells in your ear don't like degenerate in any way?
Yeah. I don't know really the details of that. Yeah, it's a, I'm not sure. Yeah. But one thing that I want to show you guys about is this this idea of a cochlear implant. Okay, and this is kind of this incredibly fascinating technology that's just became just was invented really not too long ago. But I want to show you a brief video on that to show you kind of how that works. So let's take a look at that.
Synchrony Cochlear Implant System is designed to restore hearing to individuals with severe to profound sensorineural hearing loss.
And how those work. Okay, so we talked about last time how they detect rotational movement of the head. Okay, and so the way this works, we'll kind of walk through the steps of how this works. All right, so if we start off with somebody's head being stationary, right, and then we move over to the head starting to turn. Okay, so what happens in that canal is the initial movement. The head obviously moves, but the canal itself actually moves before the fluid inside of it moves. Right, so there's a little bit of what's called fluid lag, right? Because the canal is moving, but the fluids was still, right? So the fluid lags a little bit, and this actually bends the cupula in the opposite direction that the head's moving to start with. Okay, but then eventually that fluid will kind of catch up. Okay, so if you have continuous movement of the same speed, that fluid kind of catches up, which then leads to no movement of fluid or the cupula. So eventually everything's just kind of moving together and there's really no movement of the fluid within the canal. Okay, but then as soon as that person stops turning, the fluid continues moving in the other direction, right? Because you stop and it continues moving, right? So then this pushes the cupula forwards, finally in the direction that the head was turning. Okay, and that stimulates the hair cells that way, right? So being bent one way or the other way both means things for the brain in interpreting where you're at. So I made this little image to try to kind of try to make sense of this. Okay, so if you picture yourself with a cup of coffee on your desk, okay, you're going to take that cup of coffee and just grab it and just slide it across your desk. Okay, so what would happen is the brown is going to represent the coffee itself. And so what would happen is as that cup starts moving, oh, that didn't work. Shoot, bummer. That didn't transfer over to my iPad. That was such a fun little image too. Bummer. Shoot. Yeah. So pretty much once that coffee starts moving or the cup starts moving, the coffee goes backwards, right? And you guys know that just from experiencing this, right? You can do it with your water bottle right now. If you have a clear water bottle, you go like this, the water goes backwards first, right? If you do that long enough, eventually that water will just kind of be stationary. And then when you stop, the water keeps moving forward to the other side of your bottle, right? So that's kind of the idea of the fluid lag. So we see the same thing in the hair cells as they rotate, the fluids move in the opposite way first. With constant rotation, the fluid kind of sticks with the canal, right? And then lastly, when it stops, then the fluid is now finally going the way that the head was initially moving. Okay, I got a little bit messed up. Sorry about that. But let's walk through this idea then. Okay, so let's start. We're just going to fill in which way the fluid, the cupula, and the cilia of the hair cells move versus the head movement. Okay, so if we start rotation to the left, okay, so this is really just doing this, right? We're rotating our head to the left. Okay, the fluid is going to move to the right, right? Because it lags, it goes the opposite direction, even though our head is moving to the left, right? We continue that rotation. Eventually, the fluid is going to catch up. And so then with the canal, so then the canal and the fluid all move together. All right, so even though the head's still moving left, there's really no movement of the fluid. So the cupula is not even really stimulated. Okay, but then as soon as we stop rotating, okay, the fluid keeps moving, right? And the canal is no longer moving. Okay, so then the cupula is going to be pushed the other direction. Okay, and so we can pretty much walk through those steps going the opposite way too, right? If we rotate to the right instead, first fluid's going to move to the left, the head's moving to the right. We get no movement on continued rotation. The head's still moving to the right. Then when we stop that rotation to the right, to the right, then that fluid continues moving to the right, even though the head's not moving. Okay, and the kind of interesting part about this, if you think about it, is, again, all the brain is receiving is action potentials from the neurons, right? So it gets an action potential when it goes one way. It's a different type of signal when it goes the other direction, okay? And so some of these inputs are exactly the same to the brain, right? If you look at some of those, so starting rotation to the left is going to be the same thing for the cupula as stopping rotation to the right, right? The cupula is going to be sending the exact same signal with that combo, similar to these two, right? Stopping rotation to the left, starting rotation to the right, it's going to send the same. Okay, so then the question is, how do we know which way we're spinning? Well, we have other senses, right? We have touch receptors. We have our eyes. We can see things, right? So that's where this integration of our senses comes into play big time, right? Yeah. So that's just kind of a little walkthrough of how those things are processed. So questions about those? Go ahead, Annalise. It's a great question. Yeah. So when we get dizzy, literally, if you could picture yourself like, you know, like if you did like any tire swings when you were a kid, like your friends just like spin you and you're just spinning like crazy, that fluid, as soon as you stop, that fluid is just still going like this, right? And we'll talk about it in a second, but that makes your eyes do this too. If I don't know if you've ever seen somebody who's dizzy and you look at their eyes are going back and forth like this. We'll talk about why that is in a second. But that's what being dizzy is overstimulation of that cupula, as well as some of those other receptors too. And the fluid is moving even though you're not, right? So you're totally off balance because you feel like, or your brain thinks you're moving even though you're not, right? Because the fluid's still going, right? Yeah. Okay. And then the third sensory organ here we'll talk about is the vestibule. And we kind of already walked through how this one works last class, but we'll kind of walk through it again here. So if we picture the utricle, that's the one that is parallel to the base of the skull when we're standing upright, versus the saccule, which is perpendicular to the base of the skull. You can kind of see how this one is giving us awareness of our static position and not just movement, right? Because when we're upright like this, the saccule is pulling down because those little rocks there, right? Whereas the utricle is completely flat. Okay, but then let's see if these I have little animations here too. Let's see if they work too. But if we move the head forward, there we go. I guess that one's backwards, so that's not what I meant to do. But okay. Well, it was supposed to go this way, and so then the whole thing was supposed to turn to the right. But pretty much this one would take the position of this one, right? And then this one becomes flat, right? And so then the utricle is now being bent one direction. The saccule is now upright. And so then it's that input that tells your brain that your head's like this, right? And then if we go the opposite direction, whereas this one goes back, this one comes up this way, then it's that input that tells your brain that your head's up like this, right? And so it's just these different combinations of input that are telling our brain which way that our head is positioned. Go ahead. It's supposed to be forward, yeah, so 90 degrees forwards, 90 degrees backwards, yeah. Okay, yeah, that one didn't work either. Okay, all right, and then in the same way, these things detect movement too, right? And we kind of already talked about that one. When you move forward, those little rocks come back, right? When you jump up, the ones on the side pull down. So we kind of walked through that one already on Wednesday's class. Okay, one amazing thing about all of these special senses is they all have to get put together for your brain to make sense of what's going on with your body, right? And so it's not just like one of them at a time, it's everything put together, right? So it's also, so all of this is going to the cerebellum. Okay, so it's getting information from cranial nerve 8, but then it has to integrate that with our vision, with our proprioceptors, like those muscle spindles, those Golgi tendon organs, right? The cerebellum is dealing with all of that at once for you to know what the position of your body is, right? And so then all of this is put together and then sent out as motor outputs to tighten up certain muscles so you don't fall over, loosen up other muscles so you stay put, right? So all of that's happening to maintain posture. One cool example of how this works in the cerebellum and in the semicircular canals is if you guys take the piece of paper in front of you right now, I'm going to have you do two different things. first of all, just focus on a word on your piece of paper there. And then take the paper itself or the device and move it back and forth and try to stay focused on that word. So do this, okay, without moving your head. Your head doesn't move at all, okay? It should get pretty blurry, right? It's really hard to focus on that same word, okay? But do the same, now instead, the second one is keep this still, but now just move your head back and forth and stay focused on that same word. Okay, you should have an easier time focusing on that word. And that's because your brain is receiving input from your semicircular canals that your head's moving. So then it tells your eyes to move the other direction so it stays in the right spot, right? And so kind of a cool little activity, but this is happening on a grand scale. Every time we move, right? Everything that's happening is all being integrated to do this. Okay, so just a couple things about some different disorders related to the vestibule and the semicircular canals. So one of those is vertigo. Okay, so vertigo, instability, spinning, loss of balance. Typically, this is damage to the semicircular canals themselves or damage right to that cranial nerve. Okay, there's kind of two different experiences of vertigo. Some people have one or the other, some people have both, but there's subjective vertigo, which feels like you are spinning yourself, versus objective vertigo, which when you look at something, it looks like it's moving, right? Or it feels like it's moving. Or you stand on something and it feels like that thing you're standing on is moving, right? So those are different forms of vertigo. Nystagmus is that eye movement that we were just talking about when somebody is dizzy and you look at their eyes, okay? And so if we connect that back to the tires, connect the tire swing back to what we were just talking about with moving the paper versus moving your head, when that fluid is still going around your semicircular canals fast, it's the same idea as this, like your brain thinks your head's moving, so it's trying to keep your eyes focused on something because it knows it's something, it knows your head's moving, so it's trying to keep your eyes moving, but it just bounces back from one focal point to the next. So you kind of have a mismatch of sensory inputs, right? Your inner ear is telling you you're moving, even though the rest of your body isn't, right? So your eyes are bouncing like that, and that movement is called nystagmus. Okay, so some people have this just happen to them frequently, right? So it's not just when they're dizzy, but it's just a disorder that can occur. And so this can also happen because of damage to those semicircular canals. And this can be a consequence of a severe ear infection that makes its way into your inner ear, or just spinning, becoming dizzy like we talked about. And like I said, this is a normal physiological movement. Nystagmus is when your head's moving and to help you stay focused on one thing, but it can happen when your head's not moving at all as well. Okay. Questions on any of that? Okay, so then a couple more things on balance disorders. Motion sickness. How many of you have had motion sickness in the car, on a boat? Yeah, so a lot of us have experienced that. And this is typically thought to be caused by a mismatch between visual input and inner ear input. Right, so as you're sitting in the car reading a book, right, your inner ear senses all that movement that's occurring in the car, but your eyes are telling your brain, nope, everything's perfectly still, nothing's moving because I'm looking at this book that's not moving at all, right? So there's something about that mismatch of inputs that can cause us to become sick. And there's kind of this weird connection between our cochlea and nausea and vomiting, and that tends to be the cochlea is one of the primary places that is responsible, or at least for being connected to nausea sensations. And it can also be just due to excessive sensory input, right? Just way too much stimulation of those little receptors. And then lastly, space sickness is when you don't have enough gravity to pull on those little rocks in your vestibules, right? And so they all just kind of stand straight up. And it really confuses your brain. It makes it so you really can't keep track of the position of your head anymore, because you don't have enough stimulation on those little receptors anymore. And that's kind of what's known as space sickness. Okay, questions on any of that? All right, guys, study hard for the exam on Friday, and make sure to hop on to that lab quiz right at the time that your lab starts. All right, see you guys on Friday. Come up.